All right, well, welcome back, everyone. I hope you had a good lunch. We had 6 excellent talks this morning, and we're going to start the first of the 6 very good afternoon talks. And the first one up is Myles Clark, who received his PhD on the development of a bespoke laser system. I think we all want a bespoke laser system, don't we? For the airborne atmospheric methane LiDAR from the University of Adelaide in South Australia. He joined Professor John Conklin in his Precision Space Systems lab at the University of Florida in 2018. He's worked on the development of charge management device for the LISA gravitational wave spacecraft mission, where he developed the initial digital electronics board prototypes and FPGA firmware. He also assisted with the UF CHOMP CubeSat testing in early 2018, and currently is part of the engineering team for the MIT UF CLICK mission, the subject of this presentation, which will be focusing on electronics, PCB design, and FPGA firmware management and development. Thank you.
Cool. All right, everyone can hear me? Okay, so yeah, I'm not actually a student in the student section, but I am representing the CLICK team, which is made up of a huge number of students who are all doing a lot of good work on CLICK, and hopefully are all taking a well-earned vacation, and so I'm here instead. I'm, from the Precision Space Systems Lab at the University of Florida. And before I talk about CLICK, I'm first going to go to the past/present, which is CHOMP. So CHOMP was a CubeSat led by PSSL at University of Florida, also a contender for the most patriotic acronym in general that I've ever seen. University of Florida, the football team is the Gators. They do chomping and etc. You get it. Very good. Ha ha, clap, clap, everyone. So yes, I mentioned past. So CHOMP was launched back in December of 2018 on Rocket Lab's 4th launch, actually 4th ever launch, and their first for NASA as part of the Alana program. So that's how a lot of CubeSats get up, funded through that program. It was launched to a 500-kilometer sun synchronous orbit, so it's always got power. That orbit gets about 7 years of lifetime based on drag. So it's been up there for nearly 4 years. So it's got a little bit of time left, and it is still operational. But what is CHOMP? Had time transfer in that acronym, and time transfer indeed was the mission objective. So the idea being that you want to transfer precision time from the ground to space, and then I guess back down again, possibly. So you take a laser ranging facility with its own clock, transmits a pulse of light, timing that pulse up at the spacecraft, which has its own onboard clock, and which then times it relative to its own clock. There's a retroreflector, which then sends it right back down again, timed again on the ground, and then at a later time, that information stored on the spacecraft is radioed down. That's all combined together, and you can get out the clock discrepancy via this reasonably simple algorithm formula here. How it did this was with its bespoke payload developed by PSSL, actually developed and led by students at PSSL, consisted of 2 OPTIs, the optical precision time transfer instrument. Time transfers everywhere here. And so it basically had an APD detector and all of the stuff that goes along with that for that detection. Precision oscillator, the CSAC. Unfortunately, I can't claim that I marked that off the bingo card for the PNT. It was already done earlier in the day. So the idea of that guy being that it could hold precision time, and the goal was for it to hold 20 nanoseconds over a full period orbit, so 90 minutes. And its Allen deviation was such that should be possible. A time to digital converter for actually time stamping those incoming pulses that it saw, reference to that chip scale atomic clock, then collated and collected with the course count of the clock with a TI MSP 430. Unfortunately, due to not this, but the bus having pointing issues, it was never actually able to achieve the time transfer system I just described. C'est la vie. However, you will notice that 2 of these were flown, and indeed a system was put in place that in the case that all was to go wrong, they could at least compare the clocks in space on orbit. So a question was before, how hard is it to run these CSACs? Well, after 1 year in orbit, they were compared against each other, and that's the red curve you see there. The blue curve being the same comparison in lab, and the black curve being the specifications. So the 1 year on orbit CSACs lasted, or have the same performance, if not slightly better. That's probably just, who knows, slightly better than the ones measured in lab. And they're still running to this day 4 years on. So maybe that's good PTB design on our part, or they seem to be quite robust. Anyway, so that proved that, yes, that could have done that 90-minute holdover, but yeah, alas. Anyway, so now that was the past/present, now onto the present/future. CLICK, a much more reasonable acronym, is a CubeSat laser infrared crosslink mission. So this is mostly data transfer, but also time transfer and ranging. So first, CubeSat LaserCom. What's the benefit there? So CubeSat, probably a lot of people know what CubeSat is, but it's basically a satellite made up of cubes of 10 by 10 by 10 centimeters, so 1 liter, my country's preferred unit. And then you can basically assemble them into some fraction, some number of those units. So 1U, 3U, 6U, etc. They're very useful because they have standardized equipment, standardized parts, standardized launch, and so on. So Rocket Lab will just give you a price for a certain CubeSat to get up in space. So the idea of putting a laser comm system in a CubeSat form factor with low size, weight, and power restraints that can do data transfer and time transfer could allow the realization of new sensor networks, such as synthetic aperture radar, synthetic astronomy in general, anything that requires a data link as well as time transfer link and ranging link all at the same time. So our goal with CLICK is to create a very small, low power optical transceiver capable of at least 20 megabits per second, 6 centimeters instantaneous ranging, and about 200 picosecond time transfer at about 580 kilometers of range. So what that mission looks like, it's 2 3U CubeSats, basically about the same size of a loaf of bread. In each of them is an identical payload, half of that size, so half a loaf of bread. And they both have laser transmitters with an average power of about 200 milliwatts, 2.5 centimeter receive transmit apertures, telescopes, some beacons for pointing and tracking I'll mention later. And they will transmit over a full duplex PPM link, which I will also explain in a second. And because the CLICK mission electronics inherits a lot from the chomps that came before it, it inherits a lot of the timing ability, including the CSAC and the TDC. So what that will actually look like in practice, the concept of operations, it'll get launched out. So it'll actually be ditched out of the ISS. It won't do that. This is an older one. I think they do it more precisely than throwing it. But anyway, so what it will first do is they'll kind of get into position using drag control. So basically just making themselves look big or look small to the small amount of particles at that orbit. Once they sort of get themselves into that rough position, they'll transfer the idea of where they are over radio based on sort of GPS or other positioning systems. Once they have an idea roughly of where each other are, they'll then turn on their beacon lasers, which is just a 500 milliwatt laser pointer, really. So this is not to scale. That beam will actually be about 6.5 kilometers in diameter versus the 10 by 10 centimeters. But they have very sensitive infrared cameras on them. And so they'll perform a coarse pointing, body pointing, using reaction wheels and so on to get themselves roughly aligned on that camera. Once they're roughly aligned, that light will also make it through the receive aperture, where it will feed into the fast pointing and acquisition system, which I'll explain later, which the receive and transmit beams share. And so they also get aligned in this procedure. And once that has finally locked, then the PPM encoding transmission can begin and the mission can continue, I guess. So now we'll go into all the hardware that we've currently got to get this going. This is the 3 apertures on the left there that you just saw in that video. So you got the camera down the bottom, the beacon collimator in the middle, and then the receive transmit aperture at the top there. The camera and beacon collimator are pretty self-explanatory, but on the top there, the beacon, first off, the beacon will make it through that telescope, assuming we're already roughly body pointed, bounce off a fast steering mirror, MEMS fast steering mirror, and off the first dichroic and onto a quad cell. That will form the control loop to basically get that fine pointing going. I'll explain that in more detail later. The receive beam will make it through that dichroic, through the next dichroic, and hit the APD. for reception of the pulses. And the transmitter will bounce off that second and make it through the first. And they all share the same optical paths. They're all aligned in lab before it's launched. Hopefully it doesn't move after launch. And then so that pointing matches for all of them. The actual payload in 3D, this is the sort of CAD, I think the most current CAD version of it. It's nearly 1.5U, obviously need to come in a bit because there's walls and other antennas and things that need to make the bus work. So we have to come in a little bit. So you've got the optical bench in the middle there, fiber raceway and EDFA at the bottom, and then a bunch of electronics on the back we call the electronics backstack because we're very original. In the middle there, that's that optical bench I showed you. This was a recent fit check of all of the sort of big components to make sure that you get CAD eyes. You need to make sure that the CAD eyes are actually real. We had a slight problem with the camera there. We had to take the back of the camera mount off. Oh, it fits. The APD board actually fits in that little hole you see there in the bottom right-hand corner. Then that in the whole payload, minus the fiber raceway at the bottom. Speaking of the fiber raceway, so the fiber raceway is a raceway because it's like it goes around and around and around with the fibers. It's easier to just cut them and then splice them with lots of leftover room because you always mess up like the first 10 cuts. So it basically contains all of this on some boards to control these lasers. The core of it is a tunable seed laser, which is just a CW laser. It's actually an off-the-shelf component used for like communications. You can communicate with it over a serial link, tell it which wavelength you want it to be in certain bins over a certain range. Quite useful for like calibration and such like that. But we need a shutter to turn that into pulses. So we have a silicon optical amplifier optical shutter that we trigger for our pulses. After going through a witness photodiode, that will go through our EDFA, erbium doped fiber amplifier. So this is a master oscillator power amplifier kind of situation, which is important for the PPM I'll mention later. That's another fit check with a 3D printed part. It will be milled aluminium when it's actually made, but this is just making sure that, again, CAD eyes. So if we move to the back, the optical back, that's the electronics backstack, is made up of two boards. So there's a CPU board, which is sort of like the payload, communication board, and power management, as well as the CPU board and the housing for the CSAC. And then an FPGA board that's sandwiched underneath that does all of the fast data processing, modulation, demodulation. The CSAC, sorry, the electronics, the CPU board electronics consists of a whole bunch of stuff that basically just monitors the whole system and sort of, runs the payload firmware, the payload software. It connects to the spacecraft bus at the top right corner there. Pretty much quite simple. Along the left there is the kind of the communications to the CPU, and down is the power to the FPGA. We measure current, voltage, turn things on and off. In case something sets on fire, we can turn it off. Probably won't turn back on again, but at least it won't take the whole thing down. CSAC fitting right up there. So we can get some information from it over serial communication, but mostly we just want that 10 megahertz to go straight down to that CSAC clock connector, which goes to the FPGA, which actually takes use of it. And the whole brains of the operation is just a Raspberry Pi Compute Module 3 in that DIMM slot. The FPGA board's got a little bit more going on. At the core of it is a Microsemi Smart Fusion 2. That's a hybrid FPGA. It has a Cortex M3, which we run an RTOS on, like a physical one, to kind of manage the FPGA's operation. And then the fabric's running modulator, demodulator, PAT, anything we need it to do that needs to happen fast. We got some RAM for buffering. We got a place for SD card for mass data, power connections and transmitter down the bottom, receivers up the top. Importantly, that the part at the top there, top left is the TDC and its associated electronics. That's basically an updated version of what you saw if you were paying attention to the board that Opti from Chomped. This is the version 2 of that. So onto kind of the implementation of that, of the pointing and tracking. So as I mentioned before, we have that beacon laser and that telescope. So again, we're assuming we're already coarsely pointed because that part's not quite so interesting. You just kind of point at them until the camera says go. So once it makes through that telescope, bounces off that MEMS mirror, makes it onto the quad cell. You then digitize the quad cells. So it's sine wave, but each spacecraft modulates it with a 3 kilohertz sine wave. So you digitize it, IQ demodulate it, and then calculate the centroid of that beam on that quad cell and basically just try and center that. And that loop runs That's MIT's actually. I didn't ask them how fast it runs. It's 10 kilohertz, I think, something like that. And so that feeds back to the MEMS tilt mirror to keep that point in tracking, which will also affect the TX and RX beams. So I mentioned, so onto the transmitter, I mentioned that PPM and that EDFA. Because we're trying to keep the power requirements low for a CubeSat like this, we can't just blast huge amounts of laser power because we don't have enough power to do that, and we don't have enough way to get rid of the heat. So PPM is a way of allowing us to use that amplifier and store the energy to have a constant 200 milliwatt average power, but be able to squeeze that power into small packets of pulses and get much higher peak powers to get a much better signal to noise ratio on the other side. So PPM allows us to do this by taking the data, separating it into symbols, and then those symbols vary the pulse emission time from some nominal point. So a typical setting for ClickBC might be something like PPM 16. So that's 16 symbols or 16 possible slots in which a pulse could arrive. Each slot is 10 nanoseconds wide, tau there. And then there's a guard time of 40 nanoseconds, which means there's always a minimum time that EDFA has to charge up. And that would give, based on this formula here, a data rate of 20 megabits per second. So that's exactly kind of what we were minimum hoping for. So how that actually gets encoded in a little bit more detail is you've got to start from some T0 point when you begin transmission, some global time base on the transmitter side. You take T plus the number of slots times the slot width, and you split that up into all of those slots. So that's anywhere in there is where a pulse could be transmitted. And then the guard time area where there will be no pulses, just to kind of control the pulse rate if you want to do that. For whatever reason, you might not be able to get the peak powers you want, so you may need to increase that. And then that entire time is kind of the pulse cycle time. So that's the nominal repetition rate would be from T0 to T1. And so when you want to transmit a pulse, you just calculate what the pulse delay is, the particular symbol, lowercase m there, times tau, keep the shutter open for the pulse length, and then the receiver hopefully will interpret that in the correct slot, which we'll go over later. So yes, the receiver starts with receiving those pulses that you just transmitted. So you've compressed all that 200 milliwatt power into some number of, say 4 megahertz pulse train. And now the receiver on the other side needs to receive that. So it has that APD board that goes onto that optical bench, housing things like the high voltage bias and telemetry and control systems for gain. That connects to that FPGA board via these connectors, the ribbon cable for data and power, the MCX coax for the differential signaling. And the full chain is a little like that. So the APD board contains the APD, its built-in TIA, and 2 programmable gain amplifiers. And then once it hits the FPGA board, it can then be directed in 2 different ways. It can either go to the right towards a 500 megasample 12-bit ADC, which is a possible way of decoding, but that's sort of another project for MIT to deal with. And then for me to deal with is if it gets directed to the left, where it goes to the TDC. So it actually hits 2 comparators at 2 different programmable thresholds. And each of those comparators then goes to an edge detector for a rising and falling edge, giving us 4 different events per pulse, which can be collated in the FPGA to kind of deal with any spurious signals that might come along, and also give us better precision by combining those 4 channels together. And getting the center of the pulse without as much dependence on the threshold value. So the TDC was, or one channel of the TDC was measured. So it's the TDC GPX2 made by Sciosense, previously ACAM, previously AMS. I don't know, they keep getting handed along, much like the CSAC, which is now microchip, I think. It was Symmetricom and then Microsemi. So this was basically produced by just using the FPGA board transmitter connected, shorted to its receiver electronically. So we're not using the APD board or optics here. And we just sent a constant symbol chain, so just 0, 0, 0, 0, so a nominal pulse rate of 4.5 megahertz. And then just took the difference between that. And that gave us a single shot jitter measured with all the electronics in the way of about 54 picoseconds for one channel. So that's well below our 200 picosecond requirement. Obviously, this doesn't include the optics yet. And this also includes a board that was a prototype in more ways than one. So pretty happy with that. So once you have those timestamps, you want to decode them back out into your data that the transmitter intended. So you'll get a pulse. So we're at the beginning, we're receiving some pulses. We have no idea what's going on yet, but we have a pulse. So the only thing we can do here is just time it and give it a name, T0, and we'll guess symbol 0, because why not? And the only thing we do know is that we have already pre-agreed with what the settings are, M, tau, and guard time. And so we know when the next nominal pulse should arrive. And indeed, if it does arrive in that time, then we know only one thing. We know that it was the same symbol. We don't know that it was 0 yet. But in general, we know that the next time will arrive at M times the slot width, little m being the symbol past that particular time. So if we got something like this, then if we took that delta t, divided it by the slot width, then we get our symbol out, right? Except we won't yet, because we made a probable, almost certain mistake with our guess of 0 there. So we're almost certainly going to get either a negative slot, which is not possible, or a slot larger than the number of slots there is, which is also not possible. So we do need to feed back a residual offset, an accumulated residual offset for this error. And there's also some electronic delays and such like that. And we basically do that by just accumulating the error between that delta t. So that's kind of a best case where it's a positive number. And then sort of like the perfect case of that delta t. So we bound those symbols to make sure they're in range, but we're kind of doing a floor integer division here. So if we detected a symbol of 4.5, then we call that a 4 multiplied by the slot width. And what would we as the receiver have done as the transmitter instead of what the transmitter did? And so over time, that will lock down. And indeed, the simulations show that it does that pretty quickly if you include a preamble, 0, m-1, 0, m-1, min-max, min-max. And it locks down. And then you'd go like, okay, great. So then the t measured and the t perfect will always equal 0. And then this residual will just equal the symbol offset plus some other offsets. But no, the clocks are not synchronized, right? They're two different clocks. And so they have ever so slightly different frequencies. And so what this is going to mean is that residual error that we're accumulating over time in order to do our decode is actually going to slowly track the time difference between the two clocks. And as this is exactly what Chomp was doing, except Chomp had to later do a radio communication to then pass that information down so they could compare the clocks. We have a data link, like a 20 megabit per second data link running while we're doing this. And so I don't know, put it in the packet header or something. We haven't quite decided yet. And so that's basically how we're hoping to get both data transfer and time transfer, and then ranging as well. So that's the present. That's what we're working on right now. That's almost ready to be loaded onto the next prototype board, which we just got in to attempt that outside of simulation. And so the current dates for the CLICK mission is estimated early delivery to Blue Canyon Technologies, which is our bus provider. No earlier than early 2023. That's probably a little ambitious. We had a few delays due to the pandemic and such. So we're probably going to be later than that. But the current dates are sort of early next year. We deliver the hardware, probably continue working on the software a little bit, but at least the hardware. And then a launch no earlier than late next year. Later next year. So yeah, that's the CLICK mission and where we're at. So yeah, thanks for listening. Any questions?
Do we have any questions?
Hi, yeah, I was wondering, you said you're representing the students. What of this was done by who and where?
So
And,
mostly MIT.
and you as well.
Right. Okay. So the decoding system, if you were wondering why I was going over that so detailed, that's because I've been spending a lot of my time on that. But the point in tracking, all the quad cell stuff, all the mechanical work that you saw, the two electronics boards was actually those two electronics boards are the main things that are done by myself and another research scientist at MIT. But basically everything else you saw was students. And we're basically pointing them in the right direction and giving them food to keep going.
I had a question on the hardware and then one on the software. So on the hardware, the micro semi FPGA and even the SD card, probably not generally used for space-based applications. Can you take a second to comment on like rad hard, like what you saw?
Yes. So the SD card is a probable not use. We might do it anyway, but you're absolutely right. The micro semi actually, getting into the weeds a little bit, but the micro semi FPGAs use a high voltage flash storage system on board. And so they're actually not susceptible to configuration upsets, just based on the architecture that some engineer was lucky enough to choose a while back. They are, however, very sensitive to latch up and other stuff like that. So actually those boards had way over-spec'd like power monitoring systems, because any problem, we're just going to go turn it off and turn it back on again immediately, because yeah, otherwise we could burn something.
And then on the software, on the decoding side, you had mentioned that you were investigating like a preamble for essentially just this course frame synchronization. How long does the preamble need to be? Or have you like done any?
That's another student project that they're working on. Yeah,
Gotcha.
I think 20 repeats is the current, something like that.
So this question comes from online. How long will the pair of cubes stay within range over the lifetime of the project? Just using drag, right?
Another student-led part of the mission and MIT's. So I'm not entirely sure. Yeah, I'm not entirely sure actually. They do breathe their distances, of course. And so there's only regions in which we can do the nominal 580 kilometer, but we've got stretch goals to go all the way down to 25 kilometers and all the way up to 1,000 kilometers, which if that doesn't work, NASA won't be particularly angry with us. But because of that breathing of that drag, of their natural movement, it gives us an opportunity to try all these things out.
So I came in the middle of your presentation. So if I ask for something you already presented, I apologize for that to begin with. So a few things. Number one, you mentioned about you can determine your pulse essentially to like 1 sigma of like 75 picosecond. That's just a single.
That was a differential.
Yeah,
measurement.
differential, but it's a single pulse, right? And you're also talking about, okay, using multiple symbols, you essentially are filtering, averaging. So I assume you can actually achieve much better than 75 picosecond, right? Because of all the filtering stuff, right?
Right. Yes.
So what number are you talking about then?
We'll see what we get. I mean, we have ideas, but at this point, we're trying to get the hardware delivered. So we want to get the hardware as good as it can be. And then if software can make it better, I mean, that's the Silicon Valley thing, right? But like if software can make it better than that, then so
okay, got it. Okay. Yeah. So it sounds like you have an infrastructure which allow you to achieve something much better than 75 picosecond. That's number one. Number two, obviously on the system level, there are many other things, like if you are trying to do a time synchronizing between a ground station to a moving vehicle, there's a time, if you're doing two-way post, two-way time synchronization, there's time delay issues associated with that, and because the vehicle is moving, right? That's right. Then also there's at the picosecond level, relativity become an issue too, right? Are those things being considered at all, or?
So for the spacecraft to spacecraft link, which is the main part, so it's going to be two spacecrafts. Right? That will not. There'll be Doppler problems, but not relativity problems. And there won't be two moving targets. They won't be too fast. There is, obviously, we are interested in doing downlink experiments and uplink experiments, probably mostly uplink.
So are you talking about two spacecraft in the same orbit with very, very little relative motion?
That's right.
Okay.
Yeah.
Thank you.
One last question.
One from the internet. Again, what's the next step in this research path? Application like SAR, synthetic aperture radar?
Well, I mean, so I guess if someone wants to use it for that, then yeah, yes. But actually probably some of the next versions is to kind of push more into the time transfer itself to the ground and
Okay.
sort of optimize towards that because of this ability for it to transfer information and time via a laser link, which is a very focused, non-interruptible way of doing that, right? You can't jam a laser very easily. That's of interest for reasons.
And let me do one quick question. So you're solving the PPM without using synchronization. Is there a reason why you're not using? I mean, you make your life easier, but you're wasting kind of bits. It looks like you're trying to solve for the. You don't know what zeros are and what ones are, but if you had like a synchronization sequence, you can kind of say, well, this is the start, and this sets my.
Yeah,
that's
so
my-
that's the preamble I mentioned. So you can kind of put it at the start of the frame or some start of the communication. You can sort of put a min max to try and like whack it into position to synchronize it. Yeah, and how often you have to do that, because you might have to do that at the start and then it could be stable for a very long time. It's the sort of stuff we want to try, and some students are doing simulations on this.
Okay, great. Thank you.
All right, well, let's thank our speaker one more time.